All right, so you can see this video, we're trying to determine phase angles. And if you watched the last video, we made some plots. I want to see what happens when we actually plug in that phase angle. Give me just a second to get rolling here. Click a couple of buttons here. All right, so let's get into it. Make sure that's in focus. That's as good as it's getting. All right. So what I want to do now is maybe use some other terms. I'm following along approximately with the bottom of page 7 in workbook volume 3. You can just watch this and then read page 7 after we do this, kind of as a summary to make sure it works. So in this case, this is the amplitude. I'm just changing the notation. I'm calling it X max. Why? Because we're going to have different types of oscillations. Some things are going to be periods of pendulums or maybe torsional pendulums. And so some things, instead of having an amplitude that's in meters, will have an angular amplitude. And so if we get in the habit of saying X subscript max for a horizontal oscillation, Y subscript max for a vertical oscillation, and theta subscript max for an angular oscillation, hopefully the units will become more obvious. So here's the equation for x of t and the velocity with respect to time. Boy, I'm a little tired today. And again, when we take a derivative, you might be worried about this phi changing the derivative, the phase angle phi changing the derivative, but it doesn't because it's a constant. When you take the derivative of what's inside, the derivative of this part is 0. So in this case, right, taking the derivative of cosine, you get negative sine. And then omega 0 pops out when you take the derivative of what's inside. The process for getting a phase angle when we're using these equations is usually this. There could be something else if you're trying to get it from a graph, but let's start with this. In this case, you're going to set t equal to 0 in these above equations. So from this, I see that x0 is x max. I'll call this x initial. Let's call it x0. X max. No, I'm calling it initial because that's, I called it initial over there. All right. So when we set time to 0, this is what I was trying to say about the phase angle, basically deciding where you start in the oscillation. If phi is 0, you start at x max. If phi is 180 degrees or pi radians, you start at negative x max. So that, and if it's 0, if it's pi over 2 or 90 degrees, things like that might change where the oscillation starts. Notice, let's do the same thing here. This is going to become the initial. I guess I'll erase that subscript x for now because it's an x oscillation. I don't care. If we were doing a formal lab report, we should be consistent, but we're not. We're just trying to do an example problem here. Setting t to 0, we get minus omega naught x max sine of phi. And it's important that we keep track of these minus signs. I'll mention why here. The next step, you can see we might be using inverse trig functions to figure out phi. You can tell we're going to need to do that. I'll show you more in just a minute. But watch out. The most common mistake at this step is students forget to think about both possible solutions. I'll mention that as we go through this. Basically, there's 2 possible angles that will give a correct result for this one, 2 possible angles that give a correct result for that one, and we see which result matches both of them, because only one of the 2 results will match this one. Only one of these 2 results will match one of those. More on that in a minute when we work through the example. Finally, you heard me allude to this already. It's standard to describe phase angles in degrees, even though I know we're doing calculus and we want to compute things in radians. So here is an annoying fact of life based on, not my fault, it's other people. What the common practice is, you're going to state this in degrees, but compute it in radians because this is in radians. So basically, let's just always get it in degrees and radians. That way we can describe it to people in degrees or compute with it in radians. All right. I guess the short version is it's easier to say, oh, shift it by a quarter of a period. It's easier to say shift it by 90 degrees out of 360 than 1.57 radians out of 6.28. All right, that's the logic. Let's just get to it and do the example now, please. Let's get moving here. Oh, and if we're using this, which way will this shift this thing? Let's think a minute. Or why don't I just tell you and then we'll verify it because I'm really, really tired. I just don't want to screw it up right now. Where is it? Okay. Shifts it to the left. Yes, it's winter break, the day after finals, and I'm working. What the heck am I thinking? I do not know. Anyways. All right, so this is just a fact. If we put in a positive phase angle, that's going to shift things to the left. All right, great. Let's go ahead and do this problem here. I'm trying to figure out the phase angle, and let's say I'm given this information. I know where the starting position of the spring is, or the mass in the spring. If I had this thing here and it's oscillating, right? As it's oscillating, I know the initial position and the initial velocity. Maybe I used video tracking software to figure that out. That would be a practical way to do that in the real world. So let's see what I can do here. I'm going to take a ratio and I'm going to take V initial over X initial. And then I'm going to do the same thing over here. Oops. The initial, I'm going to use the equations. And remember, X max is just the amplitude. We're trying to get used to that. What do we see dropping out? X max. So we can't get this with the information given. I think I was supposed to provide one more piece of information. I happen to know that omega naught in this problem is, what is it? 31.4. If you're wondering where I'm getting these numbers from, it's from the graph that's at the top of page 7 in the workbook. If you have that open, even though I said worry about it later. So this will match page 7. All right. So, and just so this is color coded, you can see that a little bit better. There we go. All right. Well, hopefully you can see that this is tangent. And so I see, in this case, why don't you solve this for phi really quick using algebra? I'm going to do it myself on the board. If you want to race me or if you want to hit pause, you choose. All right, here we go. I can see that tangent phi is equal to negative V initial over omega naught X initial. I'm going to take a second to verify that. I bring this omega naught down. I bring this minus sign over. I get tangent. Oh, so then phi is equal to tangent inverse of minus V. I guess I could color code it still. Got a big sneeze coming on. We'll see if I can make it through this video without sneezing. All right. That's my new goal. I just want to double check this. All right, so omega naught comes down, minus sign comes over, I get a tangent inverse. Okay, this is looking pretty good. Now, in this case, I could do a quick unit check. I have meters per second all over radians per second times meters. Radians are dimensionless. They end up getting absorbed and I get meters per second. There's no units which is correct for the argument of a trig function. All right, this is looking good. I'm going to punch in the numbers. You go ahead and punch in the numbers. Now, one thing, when we're punching in numbers, hey, for these problems, always check degrees, radians, check your mode. So right now I'm in degrees, so I'm going to first get the answer in degrees, right? We said we want to get it in both anyways. So let's go ahead and crank this in. Really important you check degrees, radians every time you go to the calculator on test. That would really stink to lose points on part A and have it just become a mess and waste a lot of time and get really confused. So always check degrees, radians. Enough said. So negative 3.14 divide by omega naught 31.4 and then divide by what was x initial 173.2. Check those units. This one's in millimeters and this one's in meters. Uh-oh, I almost screwed it up. So 1, 2, 3. So it's going to be 0.1732 meters. Always check those units. Okay, so I'm going to go back 0.1732. Okay, and now I get a negative number and I'm going to tan inverse of that. And I got negative 30 degrees. But wait, we should always check both possible solutions. So a negative tangent, if I think really quickly, right? If you're thinking about this, you've probably seen this. Some people do it cosine. What is it? Sine, cosine, and tangent are all positive in this quadrant. And then what? Sine is positive, cosine is negative, tangents negative, etc. And in this one, let's see, sine is negative, cosine is positive, tangents negative. So these are the two that have negative tangent. So we're seeing that it could be negative 30 degrees, but the other possibility would be positive 150 degrees. I'm not sure which one it is. So how can we figure that out? Give me just a second here. I need some room on the board, but basically the idea here is we might need to add or subtract 180 or something with our trig functions. More on that in a second. I'll tell you where to find that in a second. So I'm not sure which one it is. So how could we figure this out? Here's a quick way to check. Let's try plugging both of these numbers into these equations and see what we get. In particular, I know that this is a positive number, all right? Now, in this case, if I do cosine of negative 30 here, cosine of negative 30 would give me a, let's see, that's a positive number. So that's right, cosine of a negative angle. I guess what I'm saying is cosine of negative theta equals cosine of theta. The x coordinate doesn't flip. Well, now let's see what happens when we plug in here. This is a positive number. This is a positive number. Sine of a negative number would be negative, but then there's another negative here, so this would become positive. Notice if we use negative 30 degrees, I get a positive value for x initial and a positive value for b initial. You better check this because I know how to screw with you on test day, and I will, trying to see if you pay attention to both possible roots. Or sometimes I won't be paying attention and I'll make it sneaky where it's the other root. Let's confirm it is not 150. If I plug in 150, cosine of 150 is a negative number. This would be negative if I use the 150, so I would get a negative value for x initial, which doesn't match. And down here, sine of 150, let's see, sine of 150 is positive, so I get positive, 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 negative. That would give me a negative the initial. So what I was trying to say here is this. Set t equal to 0. Use inverse trig functions. Think about the other possible solutions. You might have to add or subtract 180, or if you look on page at the bottom of page 7, I tell you all the tricks for sine inverse, cosine inverse, and tan inverse, when you need to use plus or minus or add or subtract 180. All right. And then we're going to express it in degrees. So now we figured out it is not 150. That one didn't work. We figured that out by checking the signs. And so let's also get it in radians. And then I'll show you what it looks like in the graph and show you it really does shift things to the left. So when I do this, what is that? 30 times pi divided by 180. I get 0.5236. All right, now a note quick on sig figs. This one had 3 sig figs. This one had 3 sig figs. This one had 4 sig figs, but the first digit's a 1, so it's really kind of like a 3 sig fig number. So that's why I kept 3 sig figs here. I think the extra digit was 0. So, and I'll mention that this is in radians here. So I oftentimes will mark the rounding digit here, but keep the extra digit. Dong gets annoyed by this in the engineering department, but the idea is if you're doing multiple parts of a test question, I expect you to answer maybe like this, where if this was part A, you might want to include that extra digit so you avoid intermediate rounding on parts B, C, D, and E, but you indicated where you should round it, so I know you're competent. That's kind of the trade-off I do just to speed things up. I actually got this underbar trick from an old chemistry instructor many, many years ago. All right, so now let's look at the plots we made and see what should happen here. So I'm going to do a quick screen share. All right, here it is. In this case, I think the amplitude was, I'm using the example at the top of page, and I think it was whatever, I think it was 20 centimeters. I'm using the example at the top of page 7 in workbook volume 3. Top of page 7, workbook volume 3. So now I'm going to do, let me just pull up a chair. What was this thing? It was 31.4 radians per second. I'm going to delete this. And then I need phi, and I'm going to type it in degrees. And the way I get the phi symbol is F in the symbol font, SYM. And I'm going to control I for italics for the variable. I'm going to copy this, C, control V. So I'm going to get it both in degrees and radians. If you're that kind of person that's wondering, how do I get the degree symbol? Well, you can type, I don't want you to do that right now, but I guess I'll show it. Insert symbol, and you can look around for the degree symbol. There it is, insert. If you want to do that, I guess I did do it. Never mind. Okay, so that's how you could get degrees or radians. What did we say it was? I think it was -30. If I need to adjust the sig figs, kind of mess around with it here. Oh, I got lucky. It's like the first time in years I got it right. Okay, and then if I want to convert this to radians, equals radians of this angle, and it will convert it. And notice we get that. I'm going to adjust the sig figs a little bit. The nice thing about Excel is it keeps the extra digits here. Whoops. Oh, that one. Yeah, that's right. I typed it in. All right. But it keeps the extra digits even if you show it as a rounded number. So it's going to keep all those extra digits. All right. So now I think we were doing centimeters and we're doing X. All right. And we'll go centimeters per second squared. So now in this case, I'm looking up here in this function right here in the function box. I hope you could see that. All right. And what, maybe if I do this, oops, let me click in there. Hopefully you could see that on the screen. So all I need to do is add the phase angle. But now which one? I want to use radians for my computation. If I just click on that and fill down, it's not going to work. I'll show you. That doesn't quite look right. In fact, this is referencing the wrong cell. So I need to do one of two things. I either need to put in dollar signs, which I can do using F4, like that, and that makes it a constant. Or I could go up here and change the name box to phi. I kind of like that way better. And so let's see what this function looks like. So now it kind of makes sense to me. A cosine, I guess I could have called it X max, whatever. So notice that shift the plot right. I'm going to undo that and I'm going to redo it. Look which way the plot moves. I'm looking at the X of t plot right here. Okay. Whoops. I'm going to redo my change. Watch the X of t plot. It shifted to the right. Let's see what happens to the V of t plot. All we got to do is just plus phi, fill it down, shifted it to the right. Plus phi, fill it down, shifts it to the right. And now what we could do is we could see, well, what happens if you use a 90-degree phase angle? Oh, okay. How about 0? Let's start with no phase angle. All right, it's right there. The cosine's maxing out. I'm looking at the X of t graph right now, looking at the X of t graph, right? So just keep your eyes on that. I'm going to change the phase angle to 180. That should flip it upside down. What if I use 90 degrees, right? What if I use negative 90 degrees? Those are the 4 most common phase angles: 0, positive 90, negative 90, and 180. And just to be clear, look at 180 versus negative 180. They should be the same, right? Okay. So the best way to really understand a phase angle is to make this table yourself and play around with it a little bit. So, all right, you can just showing you those functions again. A cosine omega t plus phi. This one is negative omega. See that little minus sign there? Negative omega amplitude times sine omega t plus phi. And then notice there's a minus sign sitting out there as well. All right. I think that's enough on that.